Okay, then our next limit here, again, I think if we plug in, we'd get an indeterminate form. We can just use L'Hopital's rule, but the good old factor and cancel works nicely when you have a polynomial expression in the numerator and in the denominator. So factoring by product sum method, we get our numerator factored. In the denominator, factoring out a common factor of 2x, we're left with x minus 1. That works out nicely because we get rid of this term. That's the term that gave us a 0 in the denominator. And then we can just plug in. So plugging into the numerator and the denominator, our answer simplifies to negative 1/2. Okay. We have an integral inside of our limit. Let's go ahead and plug in and see what we get. So I'm going to take the limit, again, of just the numerator, because I foresee a L'Hopital's rule problem. Those happen often when you see an integral in the limit. So let's go ahead and plug in 4 for x. And when we integrate from 4 to 4, we know that that equals 0. Okay, let's take the limit as x approaches 4 of the denominator. So that would be f of 8. Do they tell us f of 8? Yes, indeed. F of 8 is 0. Okay, so we do get 0 over 0. Again, indeterminate. Okay, so let's go ahead and rewrite the original problem. When we use L'Hopital's rule, I want to show that one limit leads to the next by L'Hopital's rule. So I'm going to have that limit, the original problem, written down, and then I'm going to write by LHOP, or by L'Hopital's rule, just like before. That leads to the limit, or is equal to the limit, as x approaches 4. Now in the numerator, when I take the derivative of that integral, the integral would cancel out, and that would just leave me with f of t. In the denominator, applying chain rule, I have 2f prime of 2x. So let's plug in. So plugging in, oops, this t would actually change to an x. Sorry. So I have an f of x in the numerator. Let's plug in. We get f of 4 in the numerator. And do we know f of 4? Yes, that's 2. Okay, in the denominator, we have 2 times f prime of 4. F prime of 4 is 3. And so we get a limit of 2/6. We can reduce, not necessary though. Okay, I think we're going into some limits to infinity. We're looking for which function grows faster, the numerator or denominator. The first one, the denominator grows faster, so our limit is 0. This one, if we look at the degree, which is the largest exponent, in the numerator we have degree 1. Likewise, in the denominator, we also have degree 1. So if we have the same degree in the numerator and denominator, we look at the ratio of the leading coefficients. That's 2/3, because the 4 is under square root. Okay, let's look at the one beneath it because it's related. So the one beneath it, we're taking the limit as x approaches negative infinity. We still look at the degree. Largest exponent on top is 1 because that x squared is square rooted. Degree of 1 on the bottom. We look at the ratio of the leading coefficients, which is 3 over 1. When we go to negative infinity, we have to test to see if the limit would be positive or negative. Anything that in the numerator that's squared and then square rooted is going to be positive for the output. In the denominator, we're plugging in negative into the x, so that gives us a sign of negative. So our limit is negative 3. Okay. On the left here, this guy, I could show you a lot of different ways, by graph, by writing this as a piecewise function, but it'd just be a good one to memorize that when you're approaching 5 from the left of this function, the limit is negative 1. If we were approaching 5 from the right, the limit would be 1. This is one I asked you to memorize. That one equals 1. This is, again, I showed you at the beginning of the year algebraically why this is true, but since the limit goes to 0, and I have an x on the bottom and I have sine of 3x, I can just use this ratio as my limit. L'Hopital's rule would work on both of those previous limits also. And one final one that L'Hopital's rule does work on, but I asked you to memorize, is that that limit is equal to 0. Okay, there's a couple more practice problems we're going to do on the back of this page, so find the next video for those.